Welcome to the debate. Today, we're wrestling with a really fundamental design tension in modern C++, polymorphism. As our hardware gets more and more complex, deep instruction pipelines, multi-level caches, all that speculative execution, our old reliance on traditional OOP patterns, especially virtual functions, it feels like it's reaching a breaking point.
It really does. And that's the whole issue, isn't it? The model that worked so well for, decades? It's now in direct conflict with the reality of modern memory bandwidth. So the central question we really have to dig into, and this is coming from a lot of recent benchmarks, is, has the classic virtual function become a performance killer? Or is it still this, essential but maybe misunderstood tool?
Well, my position is that they are far from obsolete. I'd argue they're indispensable for certain really critical architectural needs. They give you benefits that, frankly, the modern alternatives just can't replicate without making things incredibly complex. And the performance hit, I think it's often way overblown, or people diagnose it as an instruction problem when it's really a memory layout problem.
I'm sorry, but I just don't buy that the performance issue is secondary. My whole point is that the measurable, definitive, performance superiority of modern value semantic models, data-oriented design, things like STD variant, it makes virtual functions fundamentally unsuitable for any performance-critical code where you actually control the types. We get better cache locality, we unlock optimizations that virtuals, they just block by design.
Okay, so let's start with the architectural necessity, because I think this gets lost in discussions that are only about CPU cycles. If you're building large frameworks or, shared libraries, your .dlls or .sos, virtual functions are the absolute foundation of application binary interface stability, ABI stability.
They are. But let's be clear about what's at stake there.
The stakes are enormous. If you build a public API around templates, or say you use std.variant in that interface, and you alter that definition, even just adding one new type, you've just broken ABI compatibility. Every single client has to stop, recompile, and redistribute. It's a disaster. But with a vtable, a library can update its own implementation, add a new method, change logic, whatever, without forcing clients to recompile, as long as that vtable layout stays put.
And that is a powerful argument, I'll give you that. For ecosystem stability, it acts like a firewall at that module boundary. I acknowledge that for, huge library distributions, that guarantee is sometimes it's worth the performance trade-off.
And it's not just that. Virtual functions solve the classic expression problem really cleanly. You get open extensibility. Third parties can derive from your base class, introduce new types, and they never have to touch your core library code. Think about plugin architectures, right? Or game engine components. That capability is it's fundamentally missing from closed set solutions like STD variant.
I see why you think that, but let me give you a different perspective, because that flexibility comes at a severe cost when we talk about speed. Let me tell you why performance today is all about memory architecture and why virtual functions are basically structured to guarantee the worst possible memory access patterns. The biggest issue is how virtual calls deal with the compiler, because the function address is figured out at runtime. It's just an opaque pointer lookup. The compiler optimizer is completely blind. It can't do fundamental things like function inlining. And if you can't inline, you can forget about other powerful optimizations like loop unrolling or auto-vectorization across that call. The gains you lose there are orders of magnitude bigger than the call itself.
The inability to inline is definitely a limitation, I agree. But the deeper architectural sin is probably the heap fragmentation.
Exactly, that's my point. Classic polymorphism forces you into using pointers and containers, right? std.vecbase. So if you have a loop running over, say, 10,000 objects, you're doing 10,000 dereferences to objects scattered all over the heap. That is pointer chasing. The memory access is completely non-contiguous.
Which guarantees cache misses.
Precisely. The CPU's hardware prefetchers, totally useless, because the next object might be sequential in your loop, but it's physically somewhere completely random in memory. So you get one L3 cache miss after another. And we know an L3 cache miss can stall a modern CPU for hundreds of cycles, maybe 400, 500 cycles.
Okay, and that brings us to the real performance debate, the scale of the hardware penalty. He started off by talking about the low-level mechanics, the double indirection of the virtual call, loading the vptr, then the function address. You called it a control hazard.
Yes, and in a really heterogeneous vector, your branch target predictor, the BTB, it just thrashes because the target address keeps changing. A single misprediction can cost you 15, 20 cycles. That's deadly for small, simple methods.
I acknowledge those cycles are real, but let me reframe the magnitude. 20-cycle branch misprediction is a mosquito bite compared to the hundreds of cycles, maybe 500, lost to a single L3 cache miss from the pointer chasing you just described. The real bottleneck is almost never the indirect branch. It is the data access pattern. When you see benchmarks showing STD variant is faster, it's almost always because it enables memory continuity, not because its own dispatch is somehow magically better at the instruction level.
But the two are tied together. Virtual functions force the bad memory layout because of object slicing. You can't just store derived objects in an std.vector base. You'd slice them. You have to use pointers, which forces heap allocations and fragmentation. std.variant, on the other hand, completely sidesteps this. It reserves enough inline storage for the largest type, and boom, you get the superior contiguous layout. It gives you performance by design.
But let's look at STD variant's dispatch for a second. It's not free either. When you use std visit, the compiler generates its own dispatch logic, usually a jump table or a big switch statement. That also relies on branch prediction.
It does, but those targets are often more predictable. And more importantly, the standard variant keeps all the data contiguous, so the dispatcher fetches the tag, makes the jump. Even if it mispredicts, fine, but when the function starts, the data it needs is already hot in the L1 or L2 cache. In the virtual function case, even with a perfect branch prediction, the first thing the function does is access memory that causes a cold cache miss. That's the critical difference.
That's a compelling argument, how virtuals enforce that fragmentation. But if we shift away from pure speed and back to maintainability, our second big point of contention, these alternatives have some serious limitations. I really challenge the scalability of value semantics when a system gets large and needs to evolve.
You're talking about the closed set problem.
Exactly. If your framework needs to support open-ended extension types defined outside your code base, standard.variant is a complete non-starter. If I add a new type to a variant in my library, I've broken the public API. Everyone downstream has to recompile everything that uses standard.visit on that variant. I mean, that's just untenable for modular or plugin-based architectures.
But that assumes everything needs open extensibility. The choice has to fit the domain. For systems where the types are known and fixed, like, say, parsing tokens in a compiler AST, or the list of materials in a game engine, the closed set nature is a feature, not a bug. It gives you exhaustive compile time checking, you get static safety and max speed in those tight loops.
But that speed advantage gets eaten up when you look at compile times in code bloat. We have to talk about the combinatorial explosion, especially with double dispatch.
The N by M problem.
Yes, I mean, imagine a collision detection system. You have 20 entity types, circle, square, whatever, and you need to handle the interaction between any two. With standard.visit on two variants, the compiler has to generate code for 20 times 20, 400 distinct code paths. Even if most of them do nothing, this leads to massive binaries, slow compile times, and it puts huge pressure on the instruction cache. What's the point of a fast jump if the code you're jumping to isn't even in the cache?
I come at it from a different way. That explosion is only a real problem if you try to build one giant monolithic visitor. Good design breaks that up. And on binary size, while templates can cause bloat, we can also trim the fat from virtual functions. If we apply the rule of zero carefully, avoiding explicit destructors and such, we can sometimes reduce the RTTI and vtable generation, which helps mitigate some of their traditional size overhead.
And while template bloat is only paid when you instantiate, in a big project, those instantiations add up fast, often way more than the fixed cost of the virtuals. It's a trade-off between architectural freedom and just a build system nightmare. If I need open extension, I either accept the runtime cost of virtuals or I face forcing everyone to recompile constantly.
Which is why the decision has to be component-specific. You don't throw out the baby with the bathwater, but you also don't use a bulldozer when you need a scalpel.
And that brings us to our third point, which is how modern C++ is trying to bridge this gap between performance and flexibility. We need models that give us that ABI stability, but with better memory patterns.
Hybrid solutions, basically.
Exactly. One of the really interesting things is the rise of better type erasure mechanisms. I'm talking about things like the optimized proxy pattern. Instead of the VPTR being buried inside a heap object, this pattern uses a non-intrusive fat pointer that lives on the stack or in contiguous memory.
So the pointer holds both the data pointer and the function table pointer separately?
That's right. By decoupling the metadata, the vtable pointer, from the scattered data object, the dispatch mechanism itself gets much better cache locality. Benchmarks have shown this can be, up to 261% faster than a traditional virtual call for small objects in tight loops, and you keep the open-ended dispatch without forcing inheritance.
That's a huge improvement, and it shows the idea of a virtual function isn't broken, just that the C++ implementation of the VPTR is maybe a bit suboptimal for today's hardware. But even that feels like a stopgap. If we look further ahead to C++26, there are language changes that could eliminate all the manual work we do for high-performance dispatch today.
You're talking about static reflection?
Yeah. The biggest pain with the visitor pattern and stead.variant right now is just how tedious and error-prone it is to write the visitors by hand. Static reflection could automate that. We could write meta functions that look at a variant's types at compile time and just generate the exhaustive switch statement for us.
Which would give us the performance and safety of std.variant without the maintenance nightmare that makes it a tough sell in big code bases right now.
And go even further. Think about metaclasses. This could totally change how we define polymorphism. Instead of being stuck with the vtable, a developer could define a metaclass that dictates how dynamic dispatch happens for a certain class hierarchy.
So you could tune the dispatch mechanism itself.
Precisely. For a closed set of types, maybe the metaclass tells the compiler to build a perfect hash map for the function addresses instead of a vtable. You decouple the performance choice from the class hierarchy. You get the abstraction of polymorphism, but you pick the best hardware interface for that specific job. That would solve your major concern about the fixed, non-optimal nature of vtables.
The idea of picking a dispatch strategy based on the context, ABI stability, raw speed, compile time safety, that is extremely compelling. It proves we need multiple kinds of polymorphism, not one winner.
Exactly. It admits that what you need for an inner loop with 10 known types is completely different from what you need for a public library that has to support types that haven't even been invented yet.
So to summarize my position, virtual functions get a bad rap as a performance killer. I think they're essential architectural tools for things that are non-negotiable, like ABI stability and open extensibility. The performance problems are really about the bad memory patterns we've historically used. The future isn't about getting rid of virtuals, but maybe using modern things like Type Erasure to get dynamic dispatch with better memory locality.
And my position holds that for the performance-critical parts of a system, the inner loops that define your throughput, the gains from value semantics and contiguous data are just too big to ignore. Data-oriented design, with tools like std.variant, has to be the default choice when you know your types. Virtual functions put up barriers to compiler optimization and cache coherence that are in those contexts simply unnecessary.
Ultimately, I think what this all shows is that high-performance C++ requires you to see polymorphism not as one single thing, but as a whole toolbox.
Right. We have to see virtuals, variants, templates, type erasure. They're all complementary tools. Each one is best for a specific constraint, whether that's raw speed, ABI compatibility, or static safety. The best architecture is the one that knows how to pick the right tool for the job.
And there is clearly a lot more to explore here as future C++ standards and hardware keep challenging our basic assumptions.